In 4.0, we are looking at the rate of change of momentum. We've dealt with this a little bit before, but we are going to study a couple different examples to see a major breakthrough that we'll have by applying the concepts of the rate of change of momentum. So in this situation, we have a cart pushed from rest. So that means that V0 equals 0, and it gets to 5 meters per second in 2 seconds. So we've got time 0, and we've got that 10 kilogram cart. So its velocity is 0, and it's going to experience a force, 10 kilograms. And then later, it is going to be moving with a velocity of 5 meters per second. And we've got 10 kilograms. And all of that occurred over a delta t of 2.0 seconds. So we could see then, if we apply our concepts, there is acceleration going on. We have a change in velocity. We have a change in momentum. We have an impulse. And that means there's a force applied over a period of time. And so what I just did there in talking through that was just mentioned all of the quantities that we know in physics so far. So let's first find out the change in momentum. So our initial momentum, P0 is mv, and the mass is 10, and the velocity is 0. So we have 0 momentum in the beginning. And then afterward, we have mv, which is 10 times 5, or we have 50 kilogram meters per second. And we could have done this way. Delta P is m delta V. So 10 times 5 minus 0 gives us 50 kilogram meters per second. Really depends if we need to know the initial and the final. So we have our change in momentum. Now we want the rate of change of momentum. Well, the rate of change of momentum is just that thing. The rate of change of anything is just that thing divided by the time it took. And so we have delta P, which is 50, and the time, which is 2. So we have 25 kilogram meters per second, which is 25 kilogram meters per second squared. And that is the rate of change of momentum. So now we look at the same situation where we've got the same cart, but it's a different person in 1 second. So we have our diagrams like this, like we had above. V0 equals 0. We've got 10 kilograms. There's going to be a force there. And at some point in time later, we know it's 1.0 seconds. That's going to be the delta t. We have a velocity of 5 meters per second, 10 kilograms. So we want to know the change in momentum and the rate of change in momentum again. So change in momentum is m delta v. And so we have 10, and let's see, we ended at 5, and we started at 0. Oh, so the change in momentum is exactly the same, which we should have intuited in this case. But the thing to keep in mind here is the only thing that determines or that brings about a change in momentum is the mass and the change in velocity. The time, we can see then, the time is irrelevant for the change in momentum. Now let's take a look at the rate of change of momentum, delta P over delta T. We have 50 over 1, which gives us 50 kilogram meters per second squared. And that's the rate of change of momentum. So we see, although the change in momentum are the same, the rates of change of momentum are different in this case. So when we look at these two situations, what is the difference in these two situations in terms of what happened? If you are one of those persons, or you and another person are each of those two persons, what's different about what you do in those situations? Well, what's different in those situations is the second one pushed harder. Second one pushed harder than the first. And what that meant was it took less time for the same delta V, which yielded a greater delta P over delta T. What's different about those two is the force applied by them. Person number 2 yielded a much greater force. In fact, a force twice as much, a force twice as large. And so, for this reason that we just saw here, this is what led Newton to define force as the rate of change in momentum. Force is the rate of change of momentum, and we can see that in this situation. Two carts going from rest to the same speed will experience the same change in momentum. What might be different is the rates. What brings about those difference in rates? Different forces being applied. So Newton says force is the rate of change in momentum. So if the rate of, we have our four-way equivalence, which is J equals F net T, delta T, equals delta P equals M delta V. So F delta T and delta P, well, if you see we rearrange that equation, then delta P equals F delta T. And so we see this relationship here. That is where that impulse definition comes from. And that force applied by a time creates an impulse. So the impulse is equal to the force times the time. That brings about a change in momentum of the object, which we see as the mass times the change in velocity. So we can now take this delta P and redefine it as M delta V for delta P, and that's all over delta T. Now, at this point, we can see this delta V over delta T, which is the acceleration.
Come, Papa.
Which is the acceleration. So that leads us to the equation F equals ma, Newton's second law. And so Newton's second law comes about from examining the momentum of objects and how we change their momentum by applying different forces leads us to the concept of force. And then we can see by connecting that back to momentum that F equals ma. And this is where F equals ma comes from. It comes from momentum. And now we can see why and we began this topic of momentum, where I said that the two paramount ideas in changes in motion are conservation of momentum and conservation of energy. And both of those are connected to force. Force is a related idea, but what drives everything with forces is changes in momentum. So force is a supporting concept to changes in momentum. And that concludes section 4.0, the rate of change of momentum. In our upcoming topic 5.0, we will take a look at the law of conservation of momentum and the different cases of the conservation of momentum.